Okay, so in the last lecture, we looked at a thought experiment where we constructed sequential Stern-Gerlach experiments, and we demonstrated that we cannot quite think of a quantum mechanical state in the same way as we think a classical state. Okay, so classically, the state of a particle is completely defined by simply telling you its position as a function of time, right? For example, Newton's laws basically tell you that F is m d square r over dt square. So if you find r as a function of t, the trajectory of a particle, then you're basically done. You have solved the dynamical problem. We cannot quite think about a quantum mechanical state in quite the same way for reasons that we explained in the last lecture, right? So quantum mechanics admits what is called a superposition of states. Superposition of states. So this is basically the statement that we made last time, that I have to look upon any state, for example, the state with plus z, as being a linear combination of something times a state with, let us say, plus x, and as something times a state with minus x. Okay, so this is what is called the superposition principle that is central in quantum mechanics. Superposition principle states that if you have two states, then a linear combination of these states of this particular form is also a valid state. Okay, to develop these ideas further and to develop them quantitatively as opposed to just a qualitative picture, one has to develop some kind of a mathematics with which one can describe these states. Okay. So the kind of mathematics that one needs to describe these states, in some sense, is both familiar and not familiar. It is familiar because you have all been exposed to the concept of vectors. It can be a little intimidating at first because we are using all these crazy new notations. For example, I can look upon this state plus z as a vector. Okay, but then why don't I just write the vector the way you usually write it, z with a arrow on top? It turns out that that notation can be a little misleading and not very useful to us. So what we will do is develop a different kind of notation, but we will also extend the notion of vectors that you have already learned to mean something else, okay, to mean something new also. So we will be studying formally what is called the concept of a linear vector space, LVS. Okay. Now, I will only touch upon those aspects of linear vector space that you would need in your quantum mechanics lecture. Prasanna would do a more complete job of it, but whatever I do in this course would be self-contained. Let me stop share and share again because it's not showing up. Okay, all right. So we will be using the notion of linear vector space. I have the chat window open, so if at any point you have any question, please type it in the chat window or unmute yourself and ask so that I can explain it to you. Okay. So let us recap what we already know about vectors, right? How do you construct a vector? Let's look upon the example of a Cartesian vector. So what is a Cartesian vector? So in two dimensions, you think of two axes called the x-axis and a y-axis, right? And we use what are called basis vectors. Basis vectors. You also call them as unit vectors sometimes. Even though the concept of basis vectors is what we would use, it's more fundamental. Basis vector is basically a vector of unit magnitude that tells you that you're traveling in either x direction or y direction. So the basis vector along the x direction you call I hat, and the basis vector along y direction you call j hat, and the basis vector along the z direction you call k hat. And you can write any vector in this two-dimensional space as the x component of this vector times the I vector and the y component of this vector along the j direction. Okay. Now you can keep extending this, right? You can also write plus the az component times the kth direction. But suppose if you look in a four-dimensional space, you can write a L component times the unit vector along the L direction, and so on and so forth. Okay, that is precisely what we will be doing in this quantum mechanics course. We will extend this notation. Okay, we will extend this concept. Okay, to 5, 6, 7, 8, 10 dimensions, 15 dimensions, or even infinite dimensions. Arbitrary number of dimensions. Also infinite dimensions. In fact, infinite dimensions is what we would be primarily interested in. Okay. So then how would we extend this notation to infinite number of dimensions? Okay. So let us actually do this step by step. A linear vector space is a kind of abstract mathematical vector space that is populated with two kinds of species, scalars and vectors. Okay. If I have this space populated by vectors and real scalars, it is called a real vector space. And if my linear vector space has vectors with complex coefficients and complex scalars, it can be a complex vector space. Okay. The real and complex part does not refer to the vector itself, but the scalars multiplying the vector. So in this case, a vector is axi plus ayj. If ax and ay are real quantities, then I say that I'm in a real vector space. If ax and ay are in general complex quantities, I live in a complex vector space. So there is two kinds of vector spaces. So when do I claim that I'm living in a vector space? So this is where things get a little abstract, but you can actually make a connection of all these things with things you already know. So the things that define a linear vector space. So suppose if I have a bunch of things that I call vectors and a bunch of things that I call scalars, can I claim that I'm living in a in a vector space? The answer to that in general is no. So to claim that we are living in a linear vector space, the vectors and scalars have to obey certain axioms. Okay. What are the axioms that the vectors and scalars have to obey in a linear vector space? So many of these, in fact, all of these are very common sense notions of what you already know. The sum of two vectors is another vector. Okay, that is basic. That does not require an explanation. For example, in this two-dimensional Cartesian space, axi plus ayj, if I have two vectors, a vector and b vector, then obviously I can write down a c vector, which is a vector plus b vector, right? The x component of the c vector is basically the x component of a plus x component of b, and the y component of c vector is the y component of a plus the y component of b. Okay, so the sum of two vectors is another vector. In the strange notation that we are using, we are calling a vector alpha not as an arrow like this, but we're enclosing the vector within a straight line like this and an angle line like this. So this is our notation for a vector. Okay, this is called a ket. This was developed by the physicist Dirac. So when I claim that I can add two vectors, I mean that I can take a vector alpha and I can take a vector beta, and the sum of vector alpha plus vector beta is another vector, which I will call some other vector gamma. Okay, just like I can write a vector plus b vector is c vector. The second rule is vector addition is commutative. it does not matter which way I add the vector. I can take alpha and add beta to it, or I can take beta and add alpha to it. It doesn't matter which way I do the addition. This is again a common sense definition. Vector addition is associative. What does this mean? This means that if I have three vectors, alpha, beta, and gamma, and I want to add them, then I can first add beta and gamma, and to that I can add alpha, or I can add alpha and beta together, and to this I can add gamma. Okay, it really doesn't matter which combination I treat first. Vector addition is associative. I can associate this with this or this combination with that particular vector. The fourth axiom is the existence of a null vector. The null vector, the symbol is 0. Okay, what does this mean? There is a null vector, a 0 vector, such that just like you have a number 0 to be, if you add any number to 0, you get the same number back. I can add any vector to the null vector and I get the same vector back. It doesn't do anything. Okay. Then the fifth rule, again, most of this should be rather straightforward. There is nothing very deep or very complicated about it, except that we are writing it in a very strange notation. Every vector that I define on this linear vector space should have an inverse vector. Okay, which means that for every alpha vector, I should have an inverse, which I will call minus alpha vector, such that if I add alpha vector to the inverse of alpha vector, I get the 0 vector. Okay, again, suppose if you have a vector which is 3i plus 4j, then I also have a vector which is minus 3i minus 4j, such that a plus minus a is 0. That is the inverse in the usual language. The product of a scalar with a vector is another vector. Again, this is also something you probably already recognize. Suppose if I have a, which is 3i plus 4j, then I can write 2 times a vector, which is 2 times 3i plus 2 times 4j, which is 6i plus 8j. That is also another vector. So the product of a scalar with a vector, a times alpha vector, is another vector which I will call some beta vector. Okay. If you have a vector space which doesn't follow any of these things, such a vector space is not, it cannot be thought of as a linear vector space. I'll give you examples as we go along. Scalar multiplication is distributive with respect to vector addition. Okay, that's just a fancy way of saying that if I have a that multiplies the combination alpha plus beta, this is the same as computing the vector a times alpha, computing the vector a times beta, and adding them together. Okay, the scalar multiplication distributes between the vectors that are being added. Scalar multiplication is distributive with respect to not just vector addition, but also scalar addition. This again means that if I have two scalars a and b, and I multiply this with a vector alpha, this is the same as constructing the vector a alpha and constructing the vector b alpha and adding them. The addition of scalars distributes with respect, sorry, the addition of scalars distributes with respect to multiplication. Okay. Then the ninth rule is scalar multiplication is associative. This is perhaps the simplest one to imagine. A times B alpha is the same as AB times alpha. It looks rather simple, but notice that the way you understand these vectors is different, right? So when I say that A multiplies B alpha, then I mean that using rule number 6, B times alpha is a vector, which I will call gamma vector. Then A times gamma vector is what I'm calculating on the left-hand side. On the right-hand side, I'm simply multiplying the two scalars together, A times B, and multiplying that with the rest with the vector alpha. It really doesn't matter which way I do it. Scalar multiplication is associative. Okay. The last, rather very simple rules are that if I have a number 0 scalar, and if I multiply it by multiplied with any vector alpha, I get the 0 vector. And if I have the number 1 and I multiply it with any vector alpha, I get the same vector again. Okay. There are very few examples where you would not be able to satisfy this. Okay. Now we have written down 10 rules. These are the rules that the objects in a vector space have to satisfy in order to be called objects in a vector space. If I claim that I'm living in a linear vector space, these are the rules that the scalars and the vectors have to obey. Now, there is a couple of points that you have to note. One, a vector is a general term. Okay. This is precisely why we do not use the notation with the arrowhead on top, because we don't simply just mean Cartesian vectors when we say vectors. Any object that satisfies these 10 rules can be called a vector. Okay, as long as these axioms are obeyed, then these objects are said to live in a vector space and they are called vectors. For example, right? So suppose if I have a set of invertible 2 by 2 matrices. Okay, I can think of these 2 by 2 matrices as vectors in a two-dimensional vector space. Okay, now this can be a little confusing, so pay attention. How can I call matrices as vectors? Matrices are different objects, vectors are different objects. That's what we have been taught up till now. But notice that if I have a set of invertible 2 by 2 matrices, and you go through axiom 1 through axiom 10, they obey all of these axioms. For example, I can take two 2 by 2 matrices, and the addition of two 2 by 2 matrices is another 2 by 2 matrix. Okay. Rule number 2, it is commutative. I can add vector A with vector B, a matrix A with matrix B, or matrix B plus matrix A. Which way I add doesn't really matter. Rule number 3 would also hold. I can take three matrices and add them with A plus B plus C or A plus B plus C. It doesn't matter. Note, I did not say multiply. Matrix multiplication is not commutative. A times B is not generally same as B times A, but we are only talking about addition here. Is there a null vector? Yes, there is a null matrix. In the case of 2 by 2 matrices, it is a matrix 0, 0, 0, 0 with all four entries 0. Okay. Existence of an inverse. Yes, of course, because I'm only worried about invertible 2 by 2 matrices. And existence of an inverse in this case is trivial, because I can think of a matrix, for example, in the 2 by 2 case, if I have a matrix with entries 1, 2, 0, 3, I can think of a matrix with entries -1, -2, 0, -3. Add these two, you get 0. Okay. So again, 6, 7, everything will go through. 8 will go through. 9 will go through. And 10 will also trivially go through. So the set of invertible 2 by 2 matrices with general form A1, A2, B1, B2 can be thought of as vectors in a two-dimensional vector space. Okay. Sorry, not a two-dimensional vector space. We'll come to the dimension of the vector space later. Okay. This can be thought of as a set of vectors in a vector space. I'll talk about the dimensions when I talk about basis. So the second point that you have to, for example, functions can also be vectors. Okay, suppose if you have a function f of x that satisfies all these axioms, then I can think of a function space as a linear vector space. We will explore this concept a little later. The other thing that you have to familiarize yourself with the bracket notation. So Dirac used the word bracket and split this up into two components, bra and ket notation. Okay, we will come to the bra a little later. The ket is basically what we have been using. Suppose if I write a vector as alpha, the way I pronounce it is ket alpha, or simply alpha vector, or whatever you want. But this notation is called ket. Okay, a bracket has two, a left-hand side bracket and a right-hand side bracket. The left-hand side bracket is called the bra, and the right-hand side angular bracket is called the ket. Okay. The bra will also be necessary, for example, when I talk about the dual vectors, which I will do so shortly. For example, n tuples of numbers. For example, if I have another example, so this is example 1. Example 2 is n tuples of numbers. What are n tuples? It's basically a set of, again, my thing is not showing. So let me stop share and share again. Give me a second. Okay, sorry about that. So n tuples of numbers is another example of linear vector space. Suppose if I have a bunch of numbers a1, a2, an that I arrange in the form of either a row vector or a column vector like this, I can take two of these n tuples and add them. For example, a1, a2 plus b1, b2 up to bn would simply be equal to a1 plus b1, a2 plus b2, an plus bn. And I can multiply this by a number, say C times A1, A2, AN is simply equal to the new n tuple CA1, CA2, CAN. So this is another example of a vector space. Okay. Ordinary vectors are also ordinary vectors that you know in 2D, 3D, 4D, anything. They are also elements of a linear vector space. So I can write any vector A as ax times I plus ay times j plus az times k. Okay. All right. But it's not always obvious that vectors live in linear vector space. For example, let us say that you are considering a subset of 3D vectors whose z component is 1. Okay. So I'm now considering a vector, any vector of the form axi plus ayj plus k vector, not az. Az is just 1. Can this be thought of as vectors living in a linear vector space? No. Why? Because if I take two such vectors, for example, if I take a vector which is equal to, let us say, 3i plus 4j plus k, and suppose if you have another vector b which is 2i plus j plus k, Remember that the z component is just 1. We are restricting our attention to those vectors whose z component is 1. And we are asking if these live in a linear vector space. Suppose if I add these two vectors, a plus b, what do I get? I get 5i plus 5j plus 2k. But the addition of these two vectors should also be in the vector space. But the addition of these two vectors creates a new vector whose z component is not 1, it is 2. Okay, so a subset of 3D vectors with az equals 1 does not satisfy, for example, the first rule that the sum of two vectors is also another vector. So even though this rule looks rather simple, notice that you can always think of examples where this rule is not obeyed. Okay, so you have to be a little careful. So there are instances, in fact, there are many instances where you would have there are instances where you would have these vectors breaking one or many of these rules. So you have to be careful. Not everything can be called as living in a linear vector space. So if I give you a homework problem saying, do these objects live in a linear vector space? You have to go through axioms 1 through axioms 10. Even though many of these can be a little straightforward, I want you to work through every one of these axioms and make sure that the objects satisfy every one of these axioms. Even if they don't satisfy one of these 10 axioms, they cannot be thought of as vectors in a linear vector space. So you have to be a little careful. Okay. In fact, we can actually go further and give you another example. This is actually another example where in a mathematical physics course you would study this in more detail. Another example is, as I told you, even functions can be thought of as belonging to a linear vector space. So for example, set of solutions to the differential equation. Let me take an example differential equation, the famous Laplace equation. Okay, Laplace equation in 2D. Okay. You can write down the general solution to this equation, which I'm not interested in doing right now, but it's actually very easy to do so. You can add two solutions and you get a third solution. Okay, all the solutions in Laplace equation also in some sense obey all the axioms of the linear vector space. Okay, so you can add two of these solutions, you get a third solution. You can multiply the solution by a scalar, it will still remain a solution, and things like that. In quantum mechanics, for example, the equation that we are more interested in is called the Schrodinger equation. And the solutions of Schrodinger equation also can be thought of as objects that live in the linear vector space, which is why we are primarily interested in the subject of linear vector space in quantum mechanics. Okay. So let me pause at this point and ask if there is any questions, because we've covered a lot of ground and I have not heard anything from any of you. So are there any questions about any of this up till this point before I move on to other concepts like basis? So let me pull out somebody. Amit.
Yes, sir.
Do you have any questions?
Sir, I have a doubt in the last example. You said that it is not linear vector space. How?
Sorry, I denote. What was the
sir, in last example, you said that it does not follow the linear vector space.
The differential equation example.
No, before it, that
it
a is equal to 3i plus 4j plus k.
Okay, all right, good. So the question is, the question is this: suppose if you have a set of three-dimensional vectors with three components, x component, some y component, but the z component is fixed to 1. Okay, so consider all possible kinds of vectors with arbitrary x component, arbitrary y component, but with the z component equal to 1. Okay, The question is, do these vectors live in a linear vector space? Okay, that is the question. The answer to this question is no. The reason the answer to this question is no is, my connection keeps failing, is because of the very first axiom of linear vector space. The very first axiom of linear vector space tells you that the addition of two vectors should also be a vector that lies in the same vector space, right? So this is the first axiom. Sum of two vectors is another vector, right? So let us go back to our example. Our example is a subset of 3D vectors with the z component equal to 1. So let us first understand, if I add two of these vectors, do I get a third vector with also z component equal to 1? The answer is no, I don't. Suppose if I have a vector A, which is 3i plus 4j plus k with z component 1, and another vector B with 2i plus j plus k with z component equal to 1, and I add these two vectors, what do I get? I get a vector which is 5i plus 5j plus 2k. So the addition of these two vectors produces a vector whose z component is not 1 but 2. So this vector does not lie in the same space as the vectors with z component equal to 1. If that is my rule, I'm only considering all the vectors with z component equal to 1, then the sum of the two of these vectors will give me a vector that is not a vector with z component equal to 1. So that vector will not have the same property as the parent vectors. So it doesn't form a linear vector space. For example, if I consider the subset of all 3D vectors with z component equal to 0, then that will be perfectly okay, because a vector is 3i plus 4j plus 0k and b is equal to 2i plus j plus 0k. If I add these two vectors, I'll get 5i plus 5j plus 0k. So the addition of two vectors also produces a vector with z component equal to 0. So I can consider a subset of three-dimensional vectors with z component equal to 0 that will form a two-dimensional vector space. But I cannot consider a subset of vectors with z component equal to 1 because that will not form a linear vector space. Is that clear?
Yes, sir, I got that.
Okay. Any other questions from anybody else?
Sir, I have a question.
Yes, please.
Does the complex vector space contain real vector space?
So complex vector space is a different space than real vector space. Suppose if all these scalars that I'm talking about, so oh my gosh, there is something really wrong with my Bluetooth today. I really apologize. I'll share again. Suppose if these A's, A, B, and these scalars that I'm talking about, if all these are complex scalars, then I'm saying that I live in a complex vector space. If I only talk about real scalars multiplying vectors, I live in a real vector space. That is all. There is nothing, this is just a nomenclature. There is nothing big about it. In general, you live in a complex vector space. In quantum mechanics, you live in a complex vector space in general. But you can also have certain examples where you can live in a real vector space. All the vectors are multiplied only by real numbers and not complex numbers. Okay?
Okay, thank you, sir.
Any other questions?
Sir, what is the mean of linear here?
Linearity simply means, so go back to this basic first thing that I mentioned. So this is a linear superposition of two states. What do you mean when you say that a thing is linear? It simply means that there's no, I'm not adding vectors at quadratic level and things like that, right? So it's a linear combination of two other vectors. Every vector can be thought of as a linear combination of other vectors. So vector A is something times a vector B plus something times a vector C plus something times a vector E. Okay, everything is appearing in a linear fashion. A set of linear transformations does not, for example, involve higher order terms, right? So for example, if you consider a transformation from variables xy to variables x1 y1 to variables x2 y2, then if x1 is equal to something times the new variable plus something else times the new variable, but nothing like plus something times the square of the new variable, then that will be not a linear transformation. If you only restrict it to first order transformations, it's a linear transformation. So this is a linear superposition of states. It's a linear vector space for that particular reason.
So, sir, we can have other power transformation also?
No, there is maybe you can mathematically. I do not know of such spaces, but they are not of any direct usefulness in physics. Okay.
Okay, sir.
Other questions?
Sir,
Yes.
so in the matrix, we are considering the matrix as vectors, and that's why the notion of inverse is different, as in case of matrices, and in case of vectors. Because in case of vectors, we simply change the components to their negatives, so that they're in the opposite direction, and that is why each scalar in the matrix becomes negative when we are considering the inverse of the
That
matrix,
is
right?
also the same case for matrices. So the inverse of a matrix. Okay. So let me be very clear. What is so again? I'll share because this thing went away. Okay. So let us go back to the definition of what an inverse is. What is an inverse? An inverse is something that you add to the original vector to get zero vector, right? So let us say that you are in the space of 2 by 2 matrices. In the space of 2 by 2 matrices, what is a zero vector? What is the definition of a zero vector? I should be able to add the zero vector to any vector and get the exact same vector back. So in a two-dimensional vector space, for example, consider that I have some vector which is a1, a2, b1, b2. What is the other matrix that I can add such that this gives me the exact same vector as before? That would simply be 0, 0, 0, 0, right? So if this is my vector, then this is my zero vector. Okay. So then in this case, what is an inverse to this matrix? It is basically a1, a2, b1, b2 plus minus a1, minus a2, minus b1, minus b2. It is precisely only this matrix which when I add to it gives me 0, 0, 0 and 0. And it is basically only this matrix, the first matrix 0, 0, 0, 0, that when I add to the initial vector gives me the same vector back again. Okay. So this is the definition of the inverse. The definition of the inverse is that vector that you add to the original vector to get the zero vector. So in the case of matrices, the inverse of this matrix is basically one with all the signs inverted.
So,
now,
but
you also need invertible matrices. That is for a different reason. We will come to that later.
okay. So that is what my question was.
So invertibility of a matrix means that the determinant of the matrix has to be non-zero. You only want to consider those matrices with non-zero determinants, and I will come to the reason why.
Okay. Okay.
Hello, sir.
Yes, please.
Should we call this additive inverse or just inverse?
Should I call this additive inverse or just inverse? That's a good question, but you can just call it additive inverse if it makes it easier for you to understand it. But the usual definition of a matrix inverse is A times A inverse is the unit matrix one, right? So that is not quite what we are saying here.
Okay, sir.
Any other questions?
Hello, sir. If we are given a linear, a vector space, and we have to find whether it follows a linear vector space or not, the 10 conditions that you defined, can't we just mix them? Like rather than having, if we just do a constant a into x plus a constant b into y, where x and y are different vectors.
Hmm.
Can't we just combine different properties to just make a few?
So the combination of this is you can always do that, but that will be a different mathematical space, and you will be imposing additional, more harder constraints if you do it that way. Okay, the simplest, straightforward way you can define them. This is the law that is given to you. If it follows these 10 axioms, it is a linear vector space. If you want to chop and change the definitions, you can always do so, but you will not be living in a linear vector space.
No, sir. I mean, we have an addition property that adding two vectors should give us two vectors, and multiplying with a scalar should give us a scalar.
Correct.
What I'm trying to say is, if we do ax plus by, then we are doing both things at the same time.
Yes and no. See, this already assumes that you know that a scalar times a vector is a vector, right? So that is also a very fundamental property. Of course, it sounds silly to you because we are all very used to this notion. But if you're going to build something from scratch, you have to spell everything out clearly. Yeah. So again, let me go back. So I should really check my Bluetooth connection. Okay. So the way you have gone through these things, the first 1, 2, 3, 4 properties, even for the first 5 properties, they don't make mention of scalars at all, right? I'm only talking about vectors and what the properties of these vectors. Then the 6th property is when I actually introduce a scalar. And I basically start introducing a scalar by claiming that if I multiply a vector by a scalar, the result is also a vector. This is a very common sense notion that you think might not be necessary. You can do away with it. That is perfectly fine. But if you're constructing a new theory mathematically from the ground up, you have to lay everything bare in a very simple fashion. That is what these rules tell you. So yes, for example, rule number 7 already assumes that rule number 6 is valid, right? Because rule number 7 says scalar multiplication is distributive with respect to vector addition. So a times alpha plus beta gives me a vector, but what this vector is a times alpha plus a times beta. But this already assumes that a times alpha is also another vector. But this statement that a times alpha is another vector is something 6 guarantees, number 6 guarantees. So you build it in a very series fashion like this. Of course, if you find that 7 is true, 6 would automatically be true. So in that sense, what you're saying is correct. When you're actually doing the checking, you can skip over one or more. But initially, I would not recommend skipping anything because sometimes you might be surprised. Does that answer your question?
Yes, sir. Okay.
So let's see. There is something in the chat window. So all these axioms are looking like field axioms as an abstract algebra. So their field axioms are completely different things. So what are field axioms? Vinay? So I do not know what the meaning of the question is. It's possible that you have seen it in a different context also. But these are actually very general kinds of all these things. Yeah. I'm not sure in what other context you have seen it, but there is the only deep thing that you have to worry about is, at least as far as whatever we're going to do is concerned, is to try and identify things that do fall in the class of linear vector spaces. Okay, the only non-trivial aspect is when I move on to functions, because it is not natural for us to think of functions as vectors, but that is precisely what quantum mechanics tells you to do. So that is the one change of a sort of a change in viewpoint that you have to embrace. That is why I'm actually belaboring all these points. See, if I only have to do A vectors and B vectors, as many of you have pointed out, many of these things are obvious, so we don't really have to spend too much of a time. But we have to move on to the idea of function spaces, where we have to think of functions as vectors. So then what is a basis vector? What is a unit vector for a function? These are all questions that you have to answer. And sometimes it is useful to have a set of basic rules if you want to sort of change your viewpoint to something completely different. So that is why I'm belaboring many of these points. Okay. Any other questions at this stage? Questions or comments? Everything okay? All right. So let us move on, and I will briefly introduce but not complete the notion of what is called basis. Again, this is fairly obvious when you think of three-dimensional vectors, but we will extend this notion to other things. What is a basis? The other thing that we want to talk about is basis and linear independence. Okay. So what is a basis set? So suppose if I have A, which is AX times I plus AY times J, I can also consider AZ times K, but I don't want to right now. Let me talk about a two-dimensional Cartesian vector space. I call these vectors I and J as unit vectors, or more appropriately, basis vectors. Why are they basis vectors? They form the basis for explaining the other vectors. For example, any other vector can be thought of as a linear combination of the I vector and J vector, right? So suppose if I have any vector that lives in this two-dimensional vector space that lives something like this, it can be thought of as something along the x-axis, this much along the x-axis, plus this much along the y-axis. That is the definition of components. So the basis vectors help us to write every vector as a linear combination of them. Okay. In our general notation, we will also use the concept of basis vectors. Just as I write A vector is AXI plus AYJ, I should be able to write down a set of basis vectors which I will call EI. Okay. How many of these are there? If I'm talking about a two-dimensional space, there is two vectors. If I'm talking about a five-dimensional space, there is five basis vectors. If I'm talking about an infinite dimensional basis space, which is what function spaces are, I'm talking about an infinite number of basis vectors. Okay. So these are the basis vectors. I should be able to write, just as I write A vector as AXI plus AYJ, I should be able to write any vector alpha as a linear combination of the basis vectors. Okay. This is a sum over alpha AI EI. This means that this is A1 times the first basis vector plus the component along the second axis times the second basis vector plus the component along the third axis times the third basis vector plus the component along the fourth axis times the fourth basis vector, and so on and so forth. If there is a finite number of basis vectors, we live in a finite dimensional linear vector space. If we have an infinite number of basis vectors, then we live in an infinite dimensional linear vector space. The quantum mechanical linear vector space called the Hilbert space is an infinite dimensional linear vector space, as we will talk about as we go along. Now, the first thing that you have to understand, and this is the last thing I will talk about today, is that there is nothing sacred about basis vectors. Okay. So suppose if I'll demonstrate this using a very simple two-dimensional example, and then we will continue talking about this on Wednesday. Let us say that I have a vector which is 2i plus j. What does this mean? Suppose if I write the components of this vector in a column vector notation, I can write this A vector as 2, 1. Okay, what this means is that along the x-axis, this has component 2, along the y-axis, this has component 1. Okay, and this is defined with respect to the ij basis. But the components of a vector depend on the choice of basis. Suppose if I am living in a different basis, the components of my vector will be different. What are the properties of a basis vector? Well, in the simple Cartesian example, the properties of the basis vector are as follows. The dot product of any of these basis vectors is 1 with themselves, but the dot product of them with another basis vector is 0. Okay. If I lived in more than one, I can also talk about the cross product of two of these vectors giving me a third vector. Anyway, so this is the basic definition the basis vectors have to satisfy. They have to have unit length I dot I is 1, and they have to be orthogonal in some sense. Okay. Unit length I dot I is 1 and orthogonal. Okay. Unit length we also called the length of this vector has been normalized to unity. Okay. The length of the vector is normalized to unity. Suppose if I have a vector whose length is not unity, I can construct a vector out of this whose length is unity by simply dividing by the square root of the length of the vector. Okay. So the basis vectors satisfy these two properties, and these two properties, they occur together. So we can club them as one term, and this term is called orthonormal. The basis vectors are orthogonal to each other and are all normalized to unity. Okay. So any set of basis vectors that are orthogonal to each other and normalized to unity can be considered as basis vectors. For example, I can think of some linear combination of I and j like this. Okay. This is not something that you normally use, but these are also a set of orthonormal basis vectors. Why? Calculate ex dot ex is 1. Why? Because it is I dot I plus j dot j divided by square root of 2 times square root of 2, which is 1 plus 1 by 2, which is 1. Also, ex dot ey, as you can easily prove to yourself, is 0. So the ex and ey are properly normalized, and ex dot ey is equal to 0, which means these two vectors are orthogonal to each other. So instead of using ij, I can use some other linear combination of I and j, and I can write this as ex and ey. Okay. Now I will leave it to you as a very small homework to work out a vector in the ex ey basis. What are the components of a vector in the ex ey basis? What would you do? You would first write ex and ey in terms of I and j, but you know already that a vector is 2i plus j. So we can invert these relations. We can invert whatever I have written in this box and write I and j in terms of ex and ey, and you can write a in terms of ex and ey, and you would find that a in terms of the ex ey basis can be written as the vector, if my calculation is right, and you should check this. Okay. Now the most important lesson is this: a vector is a vector is a vector. I am not changing a vector at all. I am simply using different basis set to express the exact same vector. The vector doesn't change. The vector is the vector. Okay. But if I express the vector using the ij basis, the components of a vector is 2 and 1. If I express the same vector using the ex ey basis, the components of the vector are something different. So in general, the components of a vector depend on the basis in which you are expressing the linear vector space. There is nothing sacred about basis. The choice of basis depends on the problem at hand. You choose the basis that makes your calculations easy. That's all. Okay. So we will explore this concept a little more as we go along. But for now, understand that the notion of a basis set for any vector space is again an extension of whatever you have learned about I vector, j vector, and k vector. But we will make this more formal as we go along.